Hello again and welcome. Today we're going to be looking at the AstroAI model M6K0R. This is a 6,000 count meter with an update rate of 3 times per second. 2-color backlight. That's interesting. I don't think we've ever seen a meter like that before. So I have yet to open this up. Comes with a little thank you card, I guess, for probably purchasing it. Again, comes with a little pamphlet. You see DC voltage accuracy. Looks like overall the ranges, it's plus or minus 0.5% reading, plus 3 digits. Overload protection is 1000 volts DC, 750 volts AC. Input impedance is 10 megaohms. AC accuracy is 0.8% of reading, plus 5 counts. Again, that looks like overall the ranges. Has a frequency response of 40 Hertz to 1 kilohertz. It does look like it's true RMS. The DC current is plus or minus 1.2% of reading, plus 3 counts. It looks like both fuses are only rated for 250 volts. So for AC current, it's plus or minus 1.5% of reading, plus 3 counts. Resistance accuracy up to 600K range is plus or minus 1% of reading, plus 3 counts. Beyond that, it's plus or minus 1.5% of reading, plus 3 counts. Looks like for capacitance, it can read up to 100 millifarads. For frequency, it looks like it can read up to 10 megahertz. For the diode test, it has a test voltage of 3 volts. Of course, it comes with the meter. And I would imagine this is just the probes. So, typical K-type thermocouple. And it looks like our normal low-end probes. Again, the cost of this meter was somewhere in the $50 range. Again, this meter came recommended to me by one of the viewers. I'm not sure. I've had this thing for probably a year now. Let's just see if it'll turn on. Oh my word. So that's kind of interesting. It's showing you with these flashing lights where to attach the leads. So if I go to current, yep, see how it's showing you where the lead should attach. Let's try milliamps. Should be across here. Yep. Huh. That's pretty slick. Let's try this colored backlight. Alright, so looking through the manual, I don't see any mention of this 2-color backlight. I think what they're referring to is the green lights that we're seeing turn on to give you the indication on where to connect the leads. You'll notice if I turn on the backlight, I push it again, you can see it just turns it on and off. And that's basically all the manual says about it. Right here, backlight, press this button to turn on and off the screen's backlight. Also does have a flashlight, so if we hold this down, you can see it is on. Alright, so before we do anything with this meter, let's just do a quick functional test. Again, we'll be using our test box for that. So this should be roughly 2.5 volts. Fairly close. Again, this is 60 Hertz, and you can see it's displaying 59.9. So this is AC coupled. Let's try it with DC coupled. So this again is switching between 0 and 5 volts now. You can see it's reading 2.5 volts still, but it cannot pick up the frequency. So to use this meter requires a 0 crossing. So here's 120 Hertz. This should read roughly 70 volts AC at about 3 kilohertz. You can see it's picking up the 3 kilohertz okay. It's showing like 42 volts or so. It's probably because of the frequency of this is up too high. Let's try it in DC mode. So again, this should be 5 volts. Looks very close. This should be about 115 millivolts. That's pretty close right there. Let's just try the meter in the frequency mode. This should pick it up without having the 0 cross. So again, this should be 60 Hertz. Well, that's interesting. So even here, it cannot pick that up. Again, we'll just insert this blocking capacitor in series with the input, like so. And now let's try it. So again, this should be 30 Hertz. And this should be 15 hertz. And this should be 120 hertz. And again, this should be 60. So it looks like as long as you don't mind using a blocking capacitor with this meter, the frequency works fine. Alright, let's try resistance. So this is going to be a dead short. Here's a 1 ohm resistor. Boy, that's pretty close. 1.0. Let's try it with a 0.1 ohm. Yeah, I'm surprised it's that accurate. This is a 0.5 ohm, 1% part. There you go. Can't complain about that. Here's 50 ohms. Again, this is a 0.01% part. Here's a 100 ohm, 0.01%. Here's a 1K ohm, 0.1%. This is a 10K ohm, 1%. This is a 100K ohm, 0.1%. This is a 1 mega ohm, 1%. This is a 10 mega ohm, 0.1%. Has some effect. Let's try it at a higher resistance. So this will be a 40 meg, 2%. This is a 100 meg, 5%. This meter cannot read conductance. Let's just try it in capacitance mode. This is a 150 picofarads. A little low. This is a 1 nanofarad. Again, a little low. It's a 0.1 microfarad. Pretty good. This is a 1 microfarad. It's pretty fast. Here's a 10 microfarad. Looks good. And here's a 100 microfarad. Looks good. Let's try continuity. So here it is with a short. You can see it has a little LED that illuminates. Let's try it in diode check mode. Here's 1 silicon diode. Here's 2 in series. Here's our white LED. You can see it lights that up just fine. And it displays roughly 2.6 volts or so. This should be roughly 500 degrees Celsius. Wonder if it'll switch the display. It does not. So Celsius, it looks like, is always in the upper right, and Fahrenheit is always the larger display. Let's crank it all the way down. Looks like about 17, and this should be about 1040 or so. You can see it over ranges. So yeah, looks like the limit is probably 1000 degrees Celsius. Right there is where it rolls over. But it appears to be working. Let's just try it in current real fast. You can see it's telling us to place it in this lead here. It should be roughly 100 microamps. You can see it's spot on. Here it is at 10. And here's 1. And this is 100 nanoamps. Again, basically 1 count of the meter. Looks good. And let's try the non-contact voltage. I'll just hold this by our cord. You can see you got to be pretty close with this one to detect it. But it does look like it's working okay. So it appears that the AstroAI is 100% functional. Let's go ahead and take this thing apart and see what it looks like inside. You can see it uses 2 AA batteries. Takes a little effort to open this up on the top side. See, the battery just attaches with the 2 spring contacts down here. I was actually expecting this to maybe have glass fuses. It's nice to see that it at least has ceramics in there. I do not know if these are sand-filled or not. They're not using chip on board. I'm quite surprised. But notice the size of the PTCs. So compare that with this PTC. Basically what ends up happening with these small PTCs is they break down. We'll actually blow the casing off of these, and at that point they present a dead short. So the transient will pass down. This probably has some clamps in it somewhere. It'll normally blow those clamps, and then we essentially wipe out the ICs that are on the board, and then the meter is no longer repairable. So if we measure from the input, that should connect to the 2 PTCs. And you can see it does, and it connects to this one here as well, and you can see the PTCs are roughly 1.16 or so, 1.14 K ohms. I believe again that these are probably the clamps. Let's see, I would imagine that this is probably the ground trace here. Yep. So yeah, this is the return path down this trace here. And from here to probably here, I gotta believe, we should get like 1.1 K. Yep. So this set of transistors here form our 1 high-speed clamp. Let's see which PTC that goes to. So it'd be from here, maybe to here. Got a 50-50 chance. Yep. So this PTC on the bottom here goes up to these high-speed clamps, only for the low voltage modes, I would imagine. So just try it in resistance, and we'll see if those are attached. Yep, right there you go. And of course, if we go to volts, for example, this should open up, which it does. The other leg looks like goes up to these resistors here. So he's got 2 of them in series, and that's our 10 meg. So these 2 resistors here would have to withstand that voltage. Of course, on the other side of this resistor here, you can see that goes straight into the IC. So there is no additional clamping circuitry for that voltage input. So what can happen here, of course, if these break down, that transient will go right into the IC, and that's going to end it. But I think what will probably happen is in the resistance mode, this PTC will probably fail. It's going to arc across. That's going to cause these 2 transistors here to blow open. That transient will probably just feed straight through to the IC at that point, and that'll be all she wrote. Well, we got it apart. Let's just see if there's any markings on these fuses. Looks like maybe a 613 at 10 amps. 250 volts. There are no markings on this side. It could be a sand-filled fuse. I'd have to open them up. This is the 10 amp jack here. Again, going through the 10 amp fuse. You can see our heavy trace working its way down. And right here is their shunt. So this is the 10 amp shunt right here, R005. Let's see if we go ahead and take the rest of this apart and have a look what the switch looks like. You can see this uses the typical springs here. Down here you can see where our two balls fell out. We'll just leave those there for now. Where's the spring popped out? Two while we're doing this. Those are a pain to put back together. What's interesting is there's no screws that actually hold the display to the circuit board. That's all done through the case. This particular meter does have some grease on it. I can tell you one thing I don't like about this right now. You'll notice that they've again placed vias right in the center of the pads. What we typically see when companies do this is the contacts work back and forth over that divot. It'll essentially cut that trace away. Contacts are pretty typical for what we see in the cheap meters. Again, this all basically looks like what I would expect. It's kind of interesting is these are the LEDs for those jack indicators, and if we look here you can see they actually have a light pipe for each one of these. Take this thing apart, you can see it's got two additional screws down here. It should expose those light pipes. You can see that whole plate just comes right off. And here are the four light pipes. Again, you can see that they've rated this meter for 1000 volts Cat 3, 600 volts Cat 4. I doubt it with these fuses in here, but hey, well, I'll go ahead and I'll put this thing back together. Alright, so let's see how the meter does reading high voltages. For this we'll just be using our ESD gun. Give us a very low current power supply. This isn't very accurate, but it'll give us an idea of what kind of voltage we're putting out. So we have the meter selected to DC. Should be roughly 480 volts. Here's a kilovolt. I mean, this is basically 1000 volts. We're applying, you can see it's basically reading 1000 volts. Let's go ahead and check out the frequency counter. So this meter claims it can read up to a maximum of 10 megahertz. And again, with 10 megahertz, it's got a 0.001 megahertz resolution. And again, this is plus or minus 3% of reading, plus 3 digits. So let's see, it's 448 right now, 0.3, and that's exactly what the RF generator is set to. Let's go ahead and increase the frequency. So let's just make this an even 1 megahertz, and you can see it's spot on. And let's try doubling this to 2, and you can see the meter is again spot on. This will be 4 megahertz. And again, it's spot on. Here we are at 8 megahertz, and it is again spot on. This is 16 megahertz. Again, it's spot on, so we have already exceeded what the meter is rated for. Let's see how high we can go up to. So here's 32. Let's just see if it has any sweet spots where it's sensitive. So 59, 60, 70 meg. Turns on the flashlight. I mean, the counter's working, but it's definitely causing some other issues with the meter. It's like 85 megahertz here. So it does appear the meter is susceptible to RF, probably in the 70 to 100 megahertz region. We're going to begin our destructive testing using our transient generator. Again, this generator can apply a full wave rectified 220 volt signal. We're just going to apply that to the meter. And our meter is reading 220 volts DC. It is correct. Now what I'm going to do is I'm just going to rotate the meter through the different settings, and we'll see if this causes any damage. And I'll just go ahead and functional test the meter. Alright, so the M6K0R passed that test just fine. What I'd like to do now is try out our grill starter. Again, this grill starter doesn't come close to matching the IEC standards, but people like to see it, so we're going to run it. Let's just see what happens. Again, we'll be applying 5 transients, both positive and negative, with the meter set to each mode, and then we'll functional test it and see if we've caused any damage. So here we go. Oops. That might be the end of it right there. Oh, she survived. So I think what we're going to do is just go ahead and continue testing, and then I'll functional test it after. Again, we'll reverse the transient. Let's just see if it's still okay. Huh, looks like it's powering up all right. Maybe just going through a reset. Alright, let's just see if it'll power back up okay. Huh, appears to. Let's just try it in resistance real quick. Reads an open. It's probably okay. Let's just try measuring a high value resistor. Let's just see here. So this is going to be our 40 mega ohm 2% part. Well, there you go. Probably no worse for the wear. Again, this is a 10 meg 0.1% part. Looks good. Measuring the temperature real fast. Again, this will be about 500 degrees. Again, that's with the knob set to the center. So at least the temperature looks good. I'll go ahead and finish up the functional test off camera. Alright, so the meter survived that test just fine. Next we're going to be using our homemade ESD gun. Again, this gun puts out a pulse that is very close to the IEC standard. Again, we'll be using this gun to apply 5 transients, both positive and negative, with the meter set to each mode. Alright, so here we go. And we have to reverse the leads to change the polarity of the transient. Let's just go ahead and make sure it powers back up. Looks like it does. Alright, that's it. Again, let's just do a real quick check. Looks like the meter does reset just fine. Let's just go to resistance. And again, it looks like it's reading an open, okay. Again, this will be our 40 mega ohm resistor. Yeah, it looks good. Alright, I'll go ahead and finish functional testing the meter, but chances are pretty good it's going to be okay. The AstroAI M6K0R survived that test just fine. Next, we're going to start our transient testing. We're going to start by applying a 1000 volt, 100 microsecond full width half height using a 2 ohm source impedance. Again, we'll be applying 5 transients, both positive and negative, with the meter set to each mode. Again, this transient generator is limited to maybe 20 joules at the most. And again, if the meter doesn't absorb that energy, it's dissipated internally of the generator. So when we're talking about this full width half height or this exponential decay pulse, that's with the output of this generator open. Alright, so again, we're going to apply 5 transients. Here we go. Again, we flip the leads to change the polarity of the transient. And that's it. I'll go ahead and functional test the meter. Alright, so the meter survived that test just fine. I've reprogrammed our generator for a 1.5 kilovolt peak. Again, there'll be a 100 microsecond full width half height with a 2 ohm source impedance. Again, we'll be applying 5 transients, positive and negative, with the meter set to each mode. Okay, that's it. I'll go ahead and functional test the meter. Alright, so the AstroAI M6K0R survived that test just fine. I've reprogrammed our generator for a 2000 volt peak, again a 100 microsecond half height, and a 2 ohm source impedance. I've tried to bring the camera in closer so if the meter does start to break down, hopefully the camera picks up that. Okay, that's it. Let's just do a real quick check here and see if the resistance still reads open. It does. And the diode check looks fine. Alright, we'll go ahead and functional test the meter. Alright, so the meter passed that test just fine. I've reprogrammed our generator for 2,500 volts peak. Again, this will be a 100 microsecond full width half height with a 2 ohm source impedance. And that's it. I didn't hear any signs of it breaking down. And again, looking at the resistance mode, it appears like it can still read and open. So I doubt the meter's been damaged, but again, we'll go ahead and functional test it. Right, our meter survived that test just fine. I've changed our generator for a 3000 volt peak, 100 microsecond full width half height, again with a 2 ohm source impedance. Again, we'll be applying 5 transients, both positive and negative, with the meter set to each mode. I'm quite surprised that the meter is doing this well with the minimal amount of transient protection that it has added. If you go back and look at the very first time I ran the $50 multimeters, very few of them survived at 3000 volts. Oh. There it went. You can see the flash. Looks like it's arcing up in this area here. Yep. That's the end of the meter right there. So that was a 3000 volt, 100 microsecond full width half height with a 2 ohm source impedance, negative going transient. I'll tell you what, let's just go ahead and take this thing apart real quick and have a look at what's going on with it. I can smell it. It looked like it's breaking down this area here. I'm guessing one of those PTCs arced over. Let's go ahead, we can hook this thing back up and let's just apply a transient and see if we can see where this is breaking down at. Alright, here we go. This is the same transient, so 3000 volts. And again, this is a negative going transient. Oh yeah, you can see it's right across the PTC here. Yeah, it's this one right here. Breaking down right across it. And because we're seeing the meter break down, what I've done is I've attached our low voltage, high energy transient generator. So again, this generator will put out about 600 joules at the most. So the way this works is this puts out a very low voltage transient. So Typically, most of the meters that I've tested would probably survive the transient off of this, but what ends up happening is if a meter breaks down like what this one's doing, what we can do is use the high voltage low energy generator to break that meter down, and then we can feed that arc with this high energy source. So we're going to try that and see what kind of damage the meter sustains. So let's go ahead and turn on the generator really quick here. And again, I'm just going to apply a single pulse and let's see what happens here. You can see even at 1,000 volts now, the meter is breaking down. Maybe you can see it here. We'll zoom in. See right up at the top in this area here. We weren't seeing that before. Again, this is only 1,000 volts. Now again, with a higher voltage transient, what we're seeing is this PTC down here will break down. So I'm going to turn up the voltage a little bit. So you can see it not only breaks down across this PTC, again, we're getting this breakdown in this area. So what we're going to be doing is using our high-speed camera, hopefully to capture this. And I think we are ready to go. You can see it really doesn't look like a lot of damage was done to it, at least on this side of the board. You can see a little bit of charring up in this area here. Maybe a little bit of charring up here. I suspect that most of the damage is probably on the back side of the circuit board. What we can do is just go ahead and remove the circuit board and have a look. Wow, look at this. So not really any damage at all. Huh. Not at all what I was expecting. So yeah, just that little bit of damage. Notice the PTC. You can see how it's broken a chunk right out of the case of this PTC. That's pretty typical of what I've seen again with these smaller PTCs. Again, this is a PTC out of a more electrically robust meter, and you can just see the size difference between the two. I think that's going to be it for this video. Hopefully you enjoyed it. So again, that was the AstroAI M6K0R. We'll catch you in the next video. Later.